All right, so this is going to be the last video in the thermodynamics section here, and this one, as the title would imply, is going to be all about Gibbs free energy. So what is Gibbs free energy? It is a value that allows us to predict if a process will be spontaneous at constant temperature and pressure. All right, and so that's going to be handy, so we know if we have to add energy into something to get it to react or produce the desired result, or if it'll just do things on its own. And so the equation for Gibbs free energy is delta G equals delta H minus T delta S. So you will notice that Gibbs is kind of the culmination of thermodynamics here, in that it involves both enthalpy and entropy in its calculation. And the conditions that define spontaneity are if delta G is less than 0 or has a negative value, the reaction is going to be spontaneous in the forward direction. If delta G is 0, then the reaction is at equilibrium, right? Hopefully you remember some things about equilibrium. And then if delta G is greater than 0 or has a positive value, the reaction will not be spontaneous in the forward direction. However, it is spontaneous in the reverse direction. Okay, standard free energy of formation. So this goes for standard enthalpy, standard entropy, though I didn't really talk about them before. We will talk about them a little bit here. So standard, right, means that we're dealing with 1 mole of a substance at standard state, described as the most stable form of a compound under the conditions of 298 Kelvin and 1 atmosphere, right? And so that goes for standard enthalpy and standard entropy, but we will also here talk about standard free energy. And the thing that denotes standard is this little circle here next to the G. So anytime you see the little circle on any of the H's, S's, or G's, that is denoting a standard free energy, enthalpy, entropy, anything like that. So that's 1 mole of a substance and standard state. And the equation that goes along with this hopefully should look very familiar by now, because it's the same equation that goes along with calculating the change in enthalpy and the change in entropy. And so it's that the change in free energy is equal to the sum of the free energy of formation of products minus the sum of the free energy of formation of reactants. So temperature is going to play a big part in whether something is spontaneous or not spontaneous, and how much free energy there is associated with this particular reaction. All right, and so for a good number of reactions, like it says here, whether or not they're spontaneous is going to depend on the temperature at which the reaction occurs. And then there's this great table here. You can find something that looks very similar in your book, but I have it here so you can write it down, because it is important to look at under what conditions things are always spontaneous or never spontaneous, and which ones you have to kind of watch out, because temperature is going to depend on whether it's spontaneous or not. I will not read through all this. I will let you pause and read through it. So a question might be something like this. All right, at what temperature does the following reaction become non-spontaneous in the forward direction? So we are looking at the formation of ammonia again from its parts, nitrogen and hydrogen, and we're going to look at what temperature this stops being spontaneous in the forward direction. So the first thing we're going to do is we're going to figure out what equation we're going to use, and we are going to use this equation where we have temperature in there, so we can figure out a temperature at which it becomes non-spontaneous. And so we have our change in energy equal to change in enthalpy minus temperature times change in entropy. And luckily, we can look up and or be given the delta H and delta S values. And so now we need to figure out exactly how we're going to go about this. And we need to remember one thing, that at equilibrium, right, Gibbs free energy is 0. And when the forward and reverse reactions are not spontaneous, meaning they are not really going to occur, they're going to cancel each other out, that is an equilibrium situation, and delta G is going to be 0. So what we can do is we can put in our values, set delta G to 0, and this is the, or these are the conditions where the temperature that allows this to happen will be the temperature at which the reaction becomes non-spontaneous in the forward direction. So now that we have all our values in there and we have our single unknown, we're going to do some good old algebra, rearrange, and solve for t, right? So the first thing we're going to do is make our equation look like this, where we have moved the 91.88 kilojoules over, and we have our negative 0.1981 kilojoules per Kelvin. And you might be saying, but Brad, delta S is 198.1 joules per Kelvin. And I'll say, yeah, you're correct, except we need these two things to be the same unit, so we convert from joules to kilojoules, and we end up with 0.1981 kilojoules per Kelvin. And so then we just do some division, and we find that this particular reaction switches from spontaneous to not spontaneous at a temperature of 463.81 Kelvin. Great. Okay. Gibbs free energy and equilibrium. I really hope you didn't think that we were done with equilibrium yet, because equilibrium just goes on forever. And so we do want to discuss how free energy and equilibrium are related. And so it's good remembering that delta G with the circle is under standard conditions, right? Concentrations of 1 mole, a temperature of 298 Kelvin, a pressure of 1 atmosphere, and that delta G equals 0 at equilibrium. So we need a way to express Gibbs free energy under non-standard conditions and non-equilibrium conditions. And if you think back to talking about equilibrium, you will remember that instead of K, which is an equilibrium constant, we use Q, which is the reaction quotient, meaning that the values you put into Q do not have to be equilibrium concentrations or pressures, right? And the same is true here. All right, so we account for this difference from standard and non-standard conditions by using the reaction quotient along with temperature, right, T, and our ideal gas constant, right? But in this case, right, remember that the ideal gas constant is not going to be liter atmospheres per mole because we are dealing with energy. So the ideal gas constant here is going to have units of joules per mole Kelvin. All right, so that's a good thing to remember, that the ideal gas constant is joules per mole Kelvin here instead of liter atmospheres per mole Kelvin. All right, and so that is one of the equations that relates Gibbs free energy and equilibrium. But you might be saying, but that's not equilibrium. That's just under non-equilibrium conditions. I thought we were going to talk about equilibrium. And so I say, okay, well, we have one here where the value of delta G is going to be 0 when things are at equilibrium. And so we have delta G under standard conditions plus RT, natural log of K. And a more useful version of this equation would be to rearrange it so we're solving for K, where K is equal to E to the delta G over negative RT, right? And that allows you to, using free energy and the temperature at which the reaction is occurring, allow you to calculate the equilibrium constant for that reaction at that temperature. Now, of course, we couldn't end this video without one more example. I'm sure you're all super excited. So the question is going to be, what is delta G under standard conditions for the following reaction? And what is the equilibrium constant for this reaction? And so again, we're going to be taking a look at the formation of ammonia. And the first thing we're going to do is calculate delta G. And so we're going to use our lovely equation for this that involves enthalpy and entropy, the values of which have been given above. We put all those in place, we do the math, and we find that the change, or the Gibbs free energy, is negative 32.8 kilojoules, which means that this reaction is spontaneous because it has a negative value. So then we're going to use that and this equation that we just learned to calculate the equilibrium constant for this reaction at 298 Kelvin. And so thinking about the units here, right, the fact that I just said a moment ago that the units of R are joules per mole Kelvin, I think you know what's coming next. We are going to convert this number from kilojoules to joules, which just a standard metric conversion will give us, negative 32,800 joules, which we will put in to this equation with our other values, which would be our ideal gas constant, which, if you remember your gas constants, when we have joules per mole Kelvin as the unit, that has a value of 8.314. And then our temperature is still 298 Kelvin. And we just do some math, and we find out that the equilibrium constant for this reaction at this temperature is 5 times 10 to the 5th. Great. And that is Gibbs free energy and the end of thermodynamics, and I will see you in class.